I had two screens before on location. Anyway, so I want to tell you a little bit about what we've done over the last 2 years or so with magnetic skyrmions. And if you don't know what magnetic skyrmions don't worry, I'll tell you a little bit what they are. So here's what I want to tell you this afternoon. I'll first tell you how you can have magnetic skyrmions in magnetic multilayer systems. And then I'll show you a couple of nice things that you can do with these skyrmions. You can actually blow them out in a process like this, which looks very much like blowing soap bubbles. Then I'll tell you a little bit about Skyrmion Hall effect, where the distinct properties of these spin textures give rise to a very specific way how they move. And then all this early work that I show here is related to skyrmions that are fairly large and easy to observe. But if you really want to do something useful, you probably want to have small skyrmions. And I'll show you a little bit how we go in that direction. And at the end, of course, I have a few brief conclusions here as well. Let me start fairly basic, actually. As many of you know, magnetism is probably one of the oldest subjects of human curiosity in some way. People have been, by some accounts, looked at it for a couple thousand years if you want so. And so you might wonder what could possibly still be new in magnetism. And it turns out the reason why magnetism is such an inspiring subject that keeps up bringing up new ideas is that you have lots of interactions that act at very different time and length scales, and they can all compete with each other. So at the fundamental level, we have, of course, atomic exchange interactions, which give rise to coupling of magnetic spins in neighboring atoms. And so this interaction, of course, acts on atomic distances and gives rise to dynamics that's very fast, like femtoseconds. But at the same time, you can have very long-range magnetic interactions, and each of us knows that. If you ever played with a magnet as a kid, you can move things at a distance. That's one of the fascinating things. And so you have these long-range dipolar interactions that microscopic length scales, and for us working in the lab, macroscopic starts at micrometers, I suppose. And the dynamics can be very slow, seconds or even longer. And the interactions at these different time and length scales can be of equal importance and can be traded off with each other. And then at the same time, in many magnetic systems, you have lots of other additional interactions due to anisotropies. If you look at crystalline materials, you can have spin-orbit interaction that couples magnetism to how electrons move in materials. You can have Zeeman interactions, which is the interactions with external magnetic fields. And you mix it all together, and it gives rise to a whole variety of very complex spin textures that have complex structure both in space and in time. And here is just a whole range of things. I'm not going to read them all to you, but these are all topics that we're interested in our group. And in particular, I want to tell you about skyrmions, how they relate. Now, before I get to skyrmions, I have to have one more little thing to mention. Namely, so the Argonne National Laboratory is a national laboratory operated by the Department of Energy. And so if we get a salary there, we have to figure out how our work relates to energy. So here's my brief little spiel on this. As you know, if you look at modern day electronics, one of the things that happens is, as you take electronic devices and you make them ever smaller, power dissipation becomes a bigger and bigger problem. And the main reason for this is that in most devices that you can think of, all the useful current goes through the bulk volume of your materials, and all the useless currents, that give rise to unwanted dissipation, goes to the surface of your materials, and they leak out of your device. And so as you make things smaller, where the ratio of surface to volume becomes larger, the amount of leakage also becomes larger and becomes more and more problem. And that gives rise to lots of heat generated in electronic devices, So if you make your micromagnetic simulation, you can now also prepare your breakfast at the same time. Or burn your lap, while you look at stuff on your laptop. And so the question is, can we address this power problem in some meaningful way using magnetism, for example? And so the first thing that you can do is you can look at, instead of having just a generic electronic current on your device, you can look at a spin polarized charge current, where normally the current is carried in equal numbers of spin up and spin down electrons, but if you involve magnetic materials, you can make it such that you prefer to have more of one spin direction carrying the current than the other. So that allows you to transport spin information at the same time as you have some charge currents going. But in terms of addressing power dissipation issues, this is still a problem because you still have a current that carries the information. So you essentially face all the same problems that you face in normal semiconductor electronics. Now you can do a little bit better by doing something which is known as a pure spin current. And one easy way how you can think of that is if you have oppositely polarized electrons moving in opposite directions, then you have a net spin current, because you move spins from here to there, but there's no net charge current involved with this. And if you look at these cartoonish pictures that are shown here, then at least in this case, you see that you can transport twice the spin information with 2/3 of the electrons involved here. So you might be able to do a little better. But at the end of the day, you're still moving electrons around. So it's not clear whether you don't encounter the same kind of dissipation problems that you encounter in pure charge-based electrons. But now you can go a step further by going to spin currents that don't rely on physically moving spin, but that are mediated by interactions between neighboring spins. And this happens if you have a magnetically ordered system. You can have, for example, spin waves where you disrupt spin at one end and then the information propagates to the other end. And now you carry spin information without actually moving spins in space. And so now the dissipation mechanisms are very different than what you have with charge transport. And so the idea is if you make use of these magnetic excitations, you may be able to actually do things more power efficient in some way. And this brings me now to why we are interested in magnetic skyrmions. In magnetic skyrmions, what we do is we take a spatially inhomogeneous spin texture and move it with the help of pure spin currents. And so that's what makes this a very efficient way of manipulating magnetic information. So magnetic skyrmions, you may wonder, okay, this is an odd name, skyrmion. Where does this come from? It comes from this guy, Tony Hilton Royle Skyrm. So this is how he looked like when he was about 20 years old. And he mostly was not so fortunate. What happened is, so this picture was taken when he got hired by Rudolf Peierls to work in Los Alamos at the Manhattan Project. So Rudolf Peierls was a British scientist, and he figured he'll hire a few other British guys. One of them was this one, Tony Hilton Royle Skyrm. The other one was a guy whose name was Klaus Fuchs. So I don't know, some are laughing. I don't know if you know who Klaus Fuchs was, but he was essentially a spy that told the Soviet Union how to build a nuclear bomb after they were done in Los Alamos. And so these two guys shared an office together. But fortunately, that didn't kill his career. So he went back to England, and in the 1960s, he came up with an idea how to model baryons, which to a guy like me, essentially is just protons and neutrons. And he had a mathematical model where these particles were modeled as what is known as topological solitons of a vector field called the pion field. You'll see a little bit about what that means in a moment. But at the time, if you worked in high energy physics, you got all excited about quarks. You didn't care about these kind of things so much. So nobody paid much attention to it until about 20 years later.
when in the 1980s, high-energy physicists finally start paying some attention to these ideas, just to get distracted again, and this time by string theory. So he did receive in 1985, though, the highest possible academic award that you can get in the United Kingdom, the Hughes Medal. But he died before he became a member of the Royal Society 2 years after that because of a surgery that went wrong. So he really was unlucky all the way. But so he certainly did not hear much about the excitement about skyrmions in terms of magnetic materials. This started about 7 years ago with neutron scattering work that was done by a group in Germany and Switzerland. They did neutron scattering, small angle neutron scattering on a material called manganese silicon. And manganese silicon was a material that was very well known to be a so-called chiral helical magnetic material, where if you are at low magnetic fields, below the ordering temperature, with just below 30 degrees, the magnetization likes to form like a helical structure. If you now apply a small, reasonable magnetic field, what happens is this helical structure kind of flips up, and you get like a conical structure that's aligned with the magnetization. And then for easily, 30, 40 years, 40 or more years, it was known that there is a different part of the phase diagram where something different happens. And this was known as the A phase, A for anomalous, because in the 1970s, nobody knew what this meant. And what happened is, in 2008, this group did some small angle neutron scattering on these materials in this A phase. And they mounted the material, well, they didn't mount the crystal the wrong way, but the field orientations were not the way they should be, and what have you. And they ended up seeing this six-fold symmetry in the scattering. And did a lot of head scratching, because this six-fold pattern was not didn't fit the crystal symmetries of the material. It's a simple cubic system in a way, and so the six-fold pattern shouldn't have been observed in the direction that they looked at. And after scratching their heads long enough, they figured out that this was really related to a magnetic structure that looks like this, where most of the magnetization is lined up with the applied magnetic field. And then you have lines of magnetization pointing in the opposite direction, and in between the magnetization points in all the other possible three-dimensional directions. And what makes this spin texture very unique is that it's topologically very different from the other possible spin textures that you have here. And it's also different from a fully polarized state. You can see this a little bit by imagining it the following way. If you have these skyrmion spin texture, where you have magnetization on the outside pointing out, on the inside pointing down, and in between all the other directions, you can project the spin texture on a unit sphere, and you see that magnetization points in every possible direction. And there's no easy transformation how you change that into it all pointing in the same direction. You can mathematically actually capture this idea by calculating a so-called topological charge. So you can take the magnetization, you plug it into this formula, and out comes a number that's either plus or minus 1. Note that the topological charge is odd. Oh, what happened there? Oh, sorry. Never mind. That the topological charge is odd in the magnetization, which means if you reverse the magnetization, the topological charge reverses sign. Since the direction of the magnetization is set by the applied magnetic field, that means if you reverse the magnetic field, you do change the sign here. Now, it's no surprise.
So, Axel,
yeah.
You can get a number larger than 1, like 2, 3.
Oh, yeah. So this is for one of the individual lines here. Now, if you have many of them, that gives you many. There's another possibility. You can have additional twists here. This you will not see in these type of materials. You can see that under other circumstances. But yeah, it could be other integer numbers too. It can be more complicated. So, but for this structure, each of these Skyrmion spin textures is associated with a fully integer plus or minus 1 topological charge. Now, and this topological charge has consequences, as you will see in my talk. Now, it's no surprise that these things were observed in these helical magnets, because in these helical magnets, you have chiral magnetic interactions that help stabilizing these spin textures. To see this, let's start with something that we're all familiar with, a simple Heisenberg ferromagnet, where the interaction between neighboring spins is just given by this dot product, and you have one constant that describes this exchange strength here. If this is positive, we know what happens. All the spins line up parallel to each other, and you get a fully ordered ferromagnetic state. Now, it turns out, if you have a material that does not have structural inversion symmetry, then you can have an additional term coupling the two spins next to each other. Besides this so-called symmetric exchange interaction, which is symmetric because it doesn't matter which way you look at the spins, you can have an antisymmetric or chiral exchange interaction. Sorry, I mean, let me fix this once and for all. Yeah. My mistake. You can have this antisymmetric exchange interaction, known as the Jarzynski-Maria interaction, that depends on the cross product of two neighboring spins. And it's called antisymmetric because if you exchange the spins, obviously this changes sign. Now, this is also the reason that if you have inversion symmetry, this has to be vanishing. This has to be 0. But if you don't have inversion symmetry, this term may exist. And here, this interaction likes spins to be either parallel or antiparallel, while this interaction prefers to have spins perpendicular to each other and with a well-defined chirality. If the first spin is like this, the next one wants to be like that, not that, or depending on the sign. What this means, if you have both of these interactions in your system, the spins are neither fully parallel to each other nor fully perpendicular. They strike like a happy medium in between, some angle in between, which just depends on the ratio of these two interactions. And hence, in these helical ordered magnetic structures, you get then these helical magnetic structures where the spin spirals in a certain way. Now, if you look careful, you see that there are as many spins pointing up as they are pointing down, and you can break that symmetry now further by applying a magnetic field which preferentially wants to have spins pointing in one direction. And in that case, you then can form these Skyrmion states. One way how you can think of it, if you have these helical waves, if you have several of them interfering, then that gives rise to these Skyrmions. So as I said, these chiral interactions help. They're not required, but it's useful to have them. And you get them when you have no inversion symmetry. And you can have this in bulk materials like manganese silicon, which is part of a family called B20 compounds, which are cubic materials where the alternating elements are alternating along the 1-1-1 direction. So you have one plane of one element, then the next plane of the opposite element, and you immediately see that the element here is different from the element there, and so there's no inversion symmetry in this material. Now, another way how to break inversion symmetry is by using multilayers. You can have that by combining a ferromagnetic material with another material that has very strong spin-orbit coupling. Let's say cobalt and platinum, or permalloy and tantalum, or there are lots of combinations, as you'll see later in my talk. And here, now at this interface, you also break inversion symmetry, and you get a Jarzynski-Maria interaction because of that. Now, why are people so excited about magnetic Skyrmions? One of the reasons is that this distinct topology has real physical implications. One of them is that gives rise to a so-called emergent field, which is directly proportional to this topological charge. And this emergent field is given just by the flux quantum divided by the size, the areal size of these skyrmions. And it turns out that if these skyrmions are small, like a few tens of nanometers, these emergent fields are very big, of the order of 100 Tesla. So how do these fields come about? If you have an electron with its spin moving through these spin textures, and let's say it locally always adjusts its spin direction to the local direction of the magnetization, then as you move an electron through a skyrmion, it means that the spin of the electron has to rotate around. So to the electron, this looks like it's exposed to a real emergent field that makes its spin rotate, and that's what this thing is. So it's not a real physical magnetic field, but it's essentially mediated by the coupling of the electron spin to the local magnetization. But there's another effect. As you move this electron now through this spin texture, this emergent field also gives rise to deflection, like a Hall effect. This is known as a topological Hall effect. But as the electron is deflected, this puts a back action on the skyrmion, and that moves the skyrmion as well. And it turns out that this is a very big handle to move a skyrmion, and it allows to move skyrmions with very low currents. In fact, if you look at bulk materials, you can see that the current densities needed to move skyrmions are 5 to 6 orders of magnitude smaller than what you need to move magnetic domain walls in thin film structures. So that's how people got very excited about the possibility to move skyrmions with very small currents. There's another aspect that facilitates the easy motion. Namely, because they are a localized structure, they can move around defects. And so if you have a skyrmion moving through material, it may easily avoid obstacles. And you can see this in micromagnetic simulations, which were done about 3 years ago in Albert Ferd's group, where they see that if you put a skyrmion in a wire and you put like a triangular defect into this wire, the skyrmion moves easily around it, and only at very low current densities it does get stuck at even these very large defects. So that seemed to suggest that this is also very robust in moving. But also, as you'll see later, defects play a role in their motion as well. But based on this, the idea was then the following. For the last 10 years, there was this idea of a magnetic racetrack memory, where you take a magnetic wire, where you can encode information in the presence or absence of magnetic domain walls. You move these magnetic domain walls with a current, and then you locally read out the magnetic structure. This is a little bit like an old-fashioned magnetic tape kind of device, except instead of moving the magnetic material, you just move the magnetic structure inside of the material. And this is an idea that was pushed by Stuart Parkin when he was still at IBM 10 years ago. Now, you can imagine that you can do the same kind of things with skyrmion spin textures. Now, what are the possible advantages? Well, we know these can be very small, of the order of 10 nanometers, so you might be able to make your devices small. You might be able to move them with very small currents, but as you'll see later, that is probably less of an advantage, because if you use low currents, they also move very slowly. So if you want a fast device, that doesn't matter that much. But I think what is more interesting is, being this localized spin texture, you can imagine to move them in 2 dimensions easily, and you can start thinking of more complex devices beyond just memories. Maybe you can do some logic kind of operations that way. Now, having said that, one of the biggest obstacles was whether you can generate skyrmions on demand, because if you want to use them to encode information, you have to be able to generate and delete them. And the first step along these lines was done 3 years ago in the group from Roland Wiesendanger in Hamburg, where they used an iron palladium film where they can locally have skyrmions, which are indicated by these red dots when they are measured with a spin polarized tunneling microscope. And then they can take the same tip that they use for measuring these, park this tip at certain locations, let's say here, have a large current pulse and generate a new skyrmion, use an opposite current pulse and delete it again. And so they can put additional skyrmions in and then remove them again. This really set things on fire, because now you can really think of using topological charge instead of electronic charge to store information and process information. Now, one problem is here it's not so clear whether the skyrmions that are generated are actually mobile, whether they can move them. These experiments were done with spin-polarized scanning tunneling microscopes, which maybe a handful of groups or so in the world really know how to use very well. It was at low temperatures, at high magnetic fields, so it wasn't necessarily very practical. So we asked ourselves, is there a different way? And so we came up with this idea of blowing magnetic skyrmions, very much like blowing soap bubbles. So in fact, this is the son of the postdoc that did the work in our group. So what his dad is doing in the lab, he's doing in the backyard there. But and in Chicago in winter, rough time. But so here's what we're doing. So we take a magnetic multilayer where we take a cobalt iron boron film and we sandwich it between tantalum and tantalum oxide. Here's a TM picture, but it doesn't really show you all that much. But what happens is, by having the oxide at the top interface, it generates a perpendicular anisotropy, which means that the magnetization likes to point perpendicular to the interfaces, which normally magnetic films don't like to do. By having tantalum underneath, we get then a Jaruzelski-Maria interaction here at this interface. And also, as you will see in a moment, it helps us to manipulate the magnetic textures with electric currents. So here you see this is the magnetization versus field of this structure. The blue is measured with fields perpendicular, the red with fields in the plane. And indeed, the magnetization likes to be out of plane. It's a very small anisotropy. But that's good because it means it gives rise to large domain structures which you can easily image. And so we can image the domain structures with what is known magneto-optic Kerr effect, which is essentially an ordinary microscope with a couple of polarizers. And you can then see the magnetic domain structures. Dark is the magnetization one way, bright is the magnetization the opposite way. And at low fields, you get these labyrinth-type striped domains, which is very common. And if you increase or decrease the field, you bias it towards one direction or the other. This is shown in more detail here for a device structure where we make a wire of this material, which is 60 micrometers wide, and it has a small constriction here of about 3 micrometers. And now what we can do is we can go to a magnetic field, kind of like here, where we have few individual stripe domains. So it's mostly bright and very few dark domains. So this is what you see here. So we have here these stripe domains. And now what we can do is we can pass a current such that the electrons move from left to right. That also pushes the magnetic domain structures from left to right. And what you will see is that these extended stripes get pushed through this constriction, and you end up with new magnetic bubbles showing up on the right-hand side. So you see this here, on occasion. So there's a constant current that is applied here. And so it whips this stripe, this band domain, into individual bubble domains, which really look like individual particles. In fact, there's an apparent repulsive interaction between them. You never see them merging. The new ones push the old ones away. And it turns out that they have exactly this skyrmion spin texture because of this Jaruzelski-Maria interaction at the interface.
Why do they come out in bursts?
Yeah, so the motion of the magnetic structures is somewhat stochastic. There are defects in the material that sometimes pin the magnetic structure and then it takes a while, some thermal activation before it gets released. That is mostly it. The current is actually a DC current in this picture. I'll show you, at the very end of my talk, I'll show you another movie with a DC current, and you do see then very well the stochastic nature of this motion. But you might also ask, well, what's going on here to begin with? Why do we see magnetization moving and all this? So in order to understand this, you have to understand two effects. One is called spin Hall effect, and the other one is spin transfer torques. Now, spin Hall effect is an idea that was postulated theoretically in the 70s of the last century. And it took a while before it really got lots of attention, but over the last 10 years it did. And the idea is the following. If you take a conducting material and you pass a current through it, then because of spin-orbit interactions, you have a different probability for a spin-up electron to scatter to the right rather than to the left, and for spin-down electrons in the opposite direction. And so by passing a current through any conductor, these spin-orbit interactions will give rise to a spin accumulation at the edges of the current-carrying wires. And this size of the spin accumulation will then depend on the magnitude of the spin-orbit interaction, and so for heavy elements, typically, it becomes very sizable. Now, what you can do then is you can combine such a heavy element, let's say tantalum, with a ferromagnetic material, and now by passing a current through this heavy element, you generate a spin accumulation at this interface with this ferromagnet. And so this non-equilibrium spin population can then interact with the magnetization in the ferromagnet and change the direction of the magnetization. And this is known then as spin transfer torque. And the spin transfer torque is most efficient if the direction of the spins is perpendicular to the magnetization, because that's how it puts a lot of torque on it. And since the spin direction is perpendicular to the current direction, this means that this effect is most efficient when the current is along the direction of the magnetization in these materials. Now, if you have a layered material where, due to the inversion symmetry breaking at the interface, you get a chiral interaction, magnetic interaction, you get a magnetic structure that rotates around like such, and if at the same time you get these spin Hall spin accumulations, they will then try to rotate all the spins in the same direction and can very efficiently move these chiral domain walls through the material. And this has been shown by two groups 3 years ago at MIT and IBM. Now, in a thin wire, we know what happens. You have a domain wall that spans across the wire, and then this domain wall just moves along the wire. What happens if you have a more extended film where we have these band domain structures? Now, as I told you, the spin transfer torque is most efficient when the magnetization is collinear with the current. That means if you have a domain structure where the magnetization in the domain wall is always perpendicular to the domain wall due to these chiral interactions, then only the tip of the domain gets affected by these currents. So only the tip moves forward, the side walls don't do anything. But if you now place such a band domain into a region where the current is inhomogeneous, now things look different. Now you have current that also goes through the side walls, not just through the tip. So you get additional spin transfer torque forces moving the domain walls. It blows up the end of this band domain wall, but then surface tension essentially takes over, just like in surface tension-driven fluid flows, such as soap bubbles or water droplets. And you get a necking instability that then rips off an individual bubble. And so you can, out of one single band domain, create as many new bubbles as you want. So we try to actually simulate this. Now, for the experts of you in the field, this is a painful simulation because, as I said, the anisotropy is small, the Jarzynski-Maria interaction is small, so all the magnetic structures are big. So you have to have a big simulation, which is computationally expensive. So we've done this here in order to make it easier. We made everything a little smaller and just put the domain wall here at the end. So it doesn't look quite like the cartoon that I showed. But if I start the simulation, what you will see is that this structure will move a little faster than here. This asymmetry is due to the Jarzynski-Maria interaction. And then there's an instability where things become very complicated. We'll switch off the current in a moment, and we'll see then that some of these structures, the domain wall goes back, and some of these structures here survive, and you have a real skyrmion that formed out of all this mess. Now, what is interesting is we did the same simulation with currents that were 10 times larger. When we did the simulations there, something curious happened. During the current, there was no well-defined domain structure anymore. The domain walls were completely destroyed. You got a mostly in-plane magnetization due to very strong spin-orbit torques. But then when we switched off the current, out of this mess, you still start condensing these skyrmion bubbles and individual bubbles here. There's one that gets eliminated at the edge, but here's a very high energetic one in the center that is very active for quite some time. So this is interesting because this suggested that there are actually two very distinct mechanisms. You can create skyrmions out of deforming a domain boundary and rip out new domain structures from that. Or you can just completely disturb the system and with much higher currents, and then you don't need any pre-existing domain structures. So we were very intrigued by that. So what we did is we took the same kind of structure where we have the tantalum, cobalt, iron boron, tantalum oxide, but removed now the center bridge and replaced it with a conducting gold bridge. Now, when we do this, we don't pass a magnetic domain structure from one side to the other. It's only a current and a large divergent current here. And lo and behold, we still see skyrmions being generated. Now, the currents are larger, so we pulse them. So there's individual current pulses, but essentially with almost all of the current pulses, we do generate new skyrmions that way out of nothing, essentially. Now, this then puts us up to really study the properties of these skyrmions in more detail. And so one thing that we were interested in is what is known as the Skyrmion Hall effect. Now, most of you, I hope, are familiar with the classical Hall effect. So if you take an electrically charged particle and you move it in the presence of a magnetic field, you have a Lorentz force acting on it, which means that the particle gets deflected sideways. And so if you have a conductor, you apply a magnetic field perpendicular by passing a current, you get a transverse voltage. And from this voltage, you can learn lots of things like the polarity of your carriers, the density of your carriers, and so on. Now, it turns out skyrmions are electrically neutral, but they have a topological charge. And this topological charge also should result in a very clear transverse force, which is called Magnus force. And it's directly proportional to this topological charge and the velocity, very reminiscent of what we see here. Now, this Magnus force is an idea that's very well known if you have rotating objects moving through air, like a soccer ball or golf ball or baseball, whatever your favorite sport is. And what happens here is because of the rotation, you have different airflow on both sides, and that puts on a transverse force. It turns out for skyrmions, this also plays a role. But before I get there, I want to say, there's one thing. This rotation of objects in air is actually very impressive. Here's an expert that can demonstrate this, Roberto Carlos. He worked, about 15 years ago for the Brazilian national team when they were still really good. and they were playing here France in a friendly game. You don't see it that much now you see it much better. You see all these guys are standing in the way, and the ball goes go, whoops. Well, it's pretty cool, actually. So you may wonder, so what does this have to do with skyrmions? Yeah? Now, when you move skyrmions in a magnetic material, actually what you do is you do locally rotate magnetic moments. So the moments are there, and you just move the magnetic texture in this magnetic material. And when you do this, interestingly, on one side of the skyrmion, the moments rotate counterclockwise, right? On this upside, if I move the skyrmion to the right, locally in the plane, the moments have to rotate counterclockwise. On the other side, they rotate actually clockwise, in order to facilitate this motion. Now, sorry, clockwise, that way. If you look at it from the perspective of the local spins, what this means is, to these spins, it looks like there's a magnetic field applied in this direction out of the plane. For these spins, it looks like there's a magnetic field pointing in the opposite direction, into the plane. So for the whole spin texture, as it moves, it does look like it's exposed to a magnetic field gradient. And this magnetic field gradient can couple to the center magnetization and result in a sideways motion of the skyrmion as such. This you can actually see in a micromagnetic simulation. Let's say you take a slab of material here, you put a skyrmion in the middle, and then if you apply a current, you see that initially it starts moving mostly sideways until it gets closer to the edge when it starts moving more towards the direction of the driving force. This can be described also by a simple equation known as the Thiele equation, where you assume that the skyrmion itself is just a rigid magnetic structure, in which case you can solve the dynamical equations for the magnetization dynamics, and you arrive at this formula, which has three terms. This one here is a term that describes the driving, the direction of which the skyrmion is pushed once you apply an electric current. And for the mechanism that are described, spin Hall effects and spin transfer torques, this direction is in the same direction as the current. Then you have a dissipative term, which depends on damping in the magnetic material, and has another prefactor that is determined by the geometry of the skyrmion. And then there's a last term, which is called a gyrotropic term, which is what gives rise to this Magnus force, and it's directly proportional to the topological charge. And just to remind you, this topological charge is odd in the magnetization. So you can change its polarity by applied magnetic fields. Now, if you look at this equation, you can actually calculate analytically the direction of the initial motion. It's given by this very simple equation here, where Vy is the transverse motion, Vx is the motion in the direction of the driving force. And so this ratio between the two is just given by 1 over alpha and d. So alpha in typical magnetic materials is 0.01. D for very small skyrmions is of order 1. So that means that the motion is really mostly transverse. So we've done this, we've done this in these materials now, but in these kind of structures, we have very inhomogeneous currents, so it's very hard to correlate the motion of the skyrmions with the actual current direction. So here we take now a wire which is flat, homogeneous, no inhomogeneities. We generate skyrmions a little bit outside here. And then what we see is, when we apply a current, all the skyrmions generated here do move at an angle with the current. And it's more or less all the same angle. So, as I said, you can take, now look, how does that depend on the topological charge? if you reverse the topological charge, the motion should be in the other way. So we can reverse the topological charge by reversing the magnetic field, which gives us opposite contrast. And lo and behold, while here the skyrmions move downwards, here they move upwards. So that works. Now, in these movies, they look like stop-action movies because that's what it is. We have current pulses, so you always see the before and after position. You don't see the skyrmion during the motion. But if we analyze these movies, we see that the motion is actually very well defined. We get like equal spaced steps in x and y direction. Now, if we reduce the current significantly below this number, then this is not necessarily true. Now, if you look at the skyrmions, they actually move mostly in the direction of the current, and there's a little bit random motion transverse to it, but not a well-defined direction transverse. And if you look at it in more detail, you do see that now the steps are much more random, much more stochastic, and they reflect just the pinning due to defects that you have in the materials automatically. Now we can look at this in more detail and look at how the angle of the direction of motion depends on the current. So this is the current applied here, the current density, and this is the Skyrmion Hall angle. So this is now for positive currents, positive fields, which gives rise to negative charges. And you see that for a wide range of currents, there's no deflection whatsoever. But then at some point, there's a finite Skyrmion Hall angle developing, and it saturates at high enough currents. If you reverse the current, the motion is in the opposite direction. And if you reverse the magnetic field, then you also get the motion in the opposite direction. Now, what happens is, in this regime, the random pinning is very important, and it reduces the sideway motion. And then if you drive it hard enough, at some point, these skyrmions don't really care so much about the pinning potentials that they see, and they really move in the direction that they want to move. And you can calculate that, as I said, from this simple equation where the transverse motion over the longitudinal motion is given by 1 over alpha d. And in our case, alpha is, as I said, around 0.01. But for large skyrmions, these skyrmions that I've shown you are about 1 micrometer. When you look at 1 micrometer size skyrmions, as d is about 60, you plug it all in here, the ratio should more or less be 1, which means that the angle should be roughly 40 degrees. Experimentally, we see something that's around 30 degrees. Given the uncertainties that we have in certain numbers, this is actually fairly reasonable. Now, there's another thing that's interesting. If you look at this, you see that this d is in the denominator. The d is a monotonous function of the size. So as we increase the size, d becomes larger. Now, when we go from smaller fields to larger fields, what we do is we compress the size of the skyrmions. They make them smaller. And indeed, we see then that the angle is larger, which is exactly what you expect from this relationship here. Now, theoretically, you see something similar. You can calculate the motion of skyrmions using numerical simulations of a particle-based model, which was done by Charles and Cynthia Olsen-Reichert in Los Alamos. And they see that similarly, the Skyrmion Hall angle has this linear dependence on driving force, which then just saturates when the driving force becomes comparable to the pinning force. Now, in the last 5 minutes, I want to tell you how we can get towards smaller skyrmions. All I've shown you so far were skyrmions in single-layer magnetic films, where the skyrmions are about 1 micrometers, which for applications is probably useless, but if you want to study their behavior, it's very easy. If you want to make it smaller, you actually have lots of room to play. All you want is you want to have a broken inversion symmetry, which means typically you have at least 3 layers. You can take a magnetic layer, sandwich it between 2 different non-magnetic layers. which gives you different spin Hall effects, different anisotropies, different Jarzynski-Maria interactions. And if you play long enough, you can make skyrmions smaller and go from micrometer-sized skyrmions to some that are just tens of nanometers. The bigger problem is, once you make them smaller, how do you know that you have skyrmions in your textures? What happens is they become very hard to detect. In bulk materials, you get skyrmions that look like this, where the magnetization circles around. And so you can easily see this with a Lorentz TEM. In thin film structures, you have something like this, which is much harder to see. So you can look at bulk materials with Lorentz TEM, where you get these Lorentz TEM images of skyrmions. But for these thin film structures, Lorentz TEM doesn't work, as I'll show you. You need other techniques, like spin polarized Lehm, for example, that tells you that you have a skyrmion texture. So what happens? Lorentz TEM is one of the prime techniques to look at skyrmions in bulk materials. And the reason is, if you have a magnetization that circles around, Lorentz TEM works on looking at how the electron path is deflected when it traverses through the magnetization. It's always deflected perpendicular to the magnetization. So for one type of skyrmion, it's deflected inwards. For the other type of skyrmion, it's deflected outwards. And you get, even when you look in plan view, a clear contrast. Now you can also have a topological trivial bubble where all the magnetization points in the same way. And here still, when you look from above, you get a clear contrast. But if you have a Néel-type skyrmion, as we have in these thin film structures, now what happens is all the electrons get deflected around the perimeter of the bubble. And so it's like you rotate everything and it just looks identical. So you get no contrast whatsoever. But now if you rotate the sample a little bit and don't look at it in plain view, you do get a little bit of contrast, but you cannot distinguish these T situations. So you can tell that they are Néel skyrmions, but you can't tell the chirality. So in order to look at smaller skyrmions, we started looking at multi-layered structures that look like this. We take a tungsten, cobalt, platinum, and repeat it several times, 5 to 8 times. You get a multi-layered structure that is structurally very good. Here are some X-rays, and I still have perpendicular anisotropy. Now, when we look in plan view, what you see here in the Lorentz TEM is actually mostly noise. But then when we tilt the structure one way or the other way, we actually get some magnetic contrast. And lo and behold, we do see then skyrmion structures here in remnants that are about 200 nanometers in size. So about a factor 5 smaller than what I showed you earlier. We can then look at the magnetic field dependence. So if we increase the field, the skyrmions shrink and they vanish at some point. So you can see then that all these skyrmions essentially vanish at the same critical diameter, which allows us then to determine properties like the Jarzynski-Maria interaction and so on. You can then play around with some of the materials between platinum, cobalt, tungsten. You can also use platinum, cobalt, iridium, for example, where you can get lots of skyrmions, very small. Some of these are down to like 80 nanometers. But you can also see that there's clearly some inhomogeneities in these multilayers. So you see lots of variation of properties, lots of variation in sizes. So this is something that still needs a lot of improvement before these materials become practically very useful. But in the meantime, it's not that difficult to make skyrmions. You can put them into complicated structures like this. And you can put a current through, and you see them moving down, up. So you can have lots of fun with it. I encourage you, have fun your own. We enjoy it. So with that, I'm pretty much at the end of my presentation. This is actually the magnetic films group at Argonne, as it was this summer. Unfortunately, lots of people moved on. But the person that was actually really in charge of this work was this guy, Wanjun Zhang. He just moved this summer to Tsinghua University and is working on things there. Here's a complete list of the people involved. As I said, Wanjun was the main driving force, but there were other postdocs like Wei Zhang, Benjamin Jungfleisch that were involved in this work. Hamid Somali was a visiting student. John Pearson, Frank Freyden, Ole Heine, Susanne Feldhaus are other senior people that were involved at Argonne. The Lawrence TM work was done by Amanda Petford's Long's group, with especially Sheng Zhang was doing most of the work. The samples in the single layer samples that I showed were grown by Gyukan Yu in Kang Wang's group at UCLA. And early on, when we did this blowing of Skyrmion bubbles, Pramil Upadhyaya and Jaroslav Tsekovniak gave us some theoretical help understanding what we were looking at. In the last part, the second last part, the Skyrmion Hall effect, Zhao Wang is a student from Bryn Mawr College that did work on that. And Jixiao Zhang and Yang Zhu did some of the micromagnetic simulations. So with that, here are my conclusions. You can generate magnetic skyrmions by using interfacial interactions, which allows to stabilize them at room temperature. If we look at these tantalum, cobalt iron boron, tantalum oxide systems, we can see that we can generate them using inhomogeneous currents. We've seen that the topological charge gives rise to a well-defined transverse motion known as the Skyrmion Hall effect. And if you go to multi-layers that are more complicated than this, then you can easily push the Skyrmion size down to below 100 nanometers while they're still stable at room temperature. With that, thank you very much for your attention.
Thank Axel for this wonderful talk. Given time limitations, let's take 1 or 2 quick questions from the audience. Yes, sir.
You talked earlier about having a low critical current for moving a skyrmion
Yes.
compared with the domain wall, but then your data showed you're using about the same kind of current density.
Yeah. So we can move things at very low current densities. Let me see. Oh, my computer is slow. If my computer would be a little faster, I could show you that we can move skyrmions at current densities that are 10 to the 4 easily. The problem is they move really slowly then too. So it's like micrometers per second. So if you want to use them in a real device, essentially you have to move them by the dimension within a nanosecond, right? Something like that. And so if they are 10 nanometers, that means they have to move at least at 10 meters per second, right? And so that we do get, but for that you have to have the higher currents. So now there's one more thing that I should say. When we have the skyrmions as large as what I've shown here, then all the forces that move them are essentially exactly the same as the ones that move domain walls. The fact that they have a distinct topology just changes the direction in which they move, but other than that, they don't move any faster because of it. Now, what I mentioned with these emergent fields and how they relate to skyrmion motion, that becomes much more important when you make the skyrmion much smaller. At 1 micrometer size, these emergent fields are like 5 Ørsted. That's not really important. But if you manage to make them down 10 nanometers, it's possible that you can move them even more efficiently. And then maybe you can move them faster than you could do an ordinary domain wall. But that's not clear at this point. So the low depinning current, I think, is a relatively minor advantage, if even an advantage at all.
Following Sarah's question, so to achieve a similar orders of magnitude of the skyrmion velocity, we actually need similar magnitude of current density?
Yeah, so certainly for all the systems investigated so far, that is true. I mean, we are mostly limited in the speed by the size of our devices and the resistivity of our films, and well, the voltage that we get out of our pulse generator. But I know the groups in Mainz and in MIT, they've demonstrated speeds up to 100 meters per second also for skyrmions. So I don't think there's any fundamental reason why they would move any slower or faster. Well, if you make them very small, maybe they move faster, but other than that.
Here in the beginning, you described some kind of transformation of a planar skyrmion into some kind of a spherical type object.
Oh.
And didn't really understand what that transformation was, but so I wanted to ask, what is the significance of turning one of these things into a sphere?
Okay, so this is, no, sorry, one more. This is not really a transformation, it's just a projection. If you take this two-dimensional spin texture and project it on a unit sphere, where you take the center of the skyrmion as one of the poles and the edge of the skyrmions as the other pole of the sphere, then you can project this whole spin texture on top of a sphere, and somebody who's mathematically inclined finds it then easier to see that the topology is distinct. For some people it's helpful, for some others it's not. It's just the mathematical projection.
Okay, but it doesn't have anything to do with the physics you've been describing.
No, not at all.